All right. Hello, everybody. Today I'm going to be talking a bit about a tool/framework that we use often in fisheries science, and I'm really interested to see if we can get some kind of exercises going where we have discussions where we see if this kind of approach can apply to other systems. So I'm going to try to start general, zoom in on fisheries science, and then see if we can zoom back out and if there are applications for how this kind of approach can be used in other systems. So the title of my talk is A Management-Oriented Approach for Coupled Human Environmental Systems, with a focus on management strategy evaluation in fisheries science. So a primary motivation and what creates the need for forecasting and decision making is usually some sort of coupled human environment system. And it goes by lots of names depending on the field you're in. In my field, you might call it like a paired or coupled social ecological system, or it might be a natural resource management system. But the essence of it is that you have some complex natural system, and then you have some complex human system that is making decisions. And I also want to point out that I do think our kind of healthcare examples fit in here, because I do think that a human disease system can be a complex natural system. But the crux of it is that you've got this paired decision-making human system. So essentially you have information that flows out of that complex natural system. So that might be like survey data from an ecological system, or disease rate system from a human system. And then essentially some sort of human modification flows back in the form of some sort of regulation or rules or effect, say if you're fishing or you're logging. So the way that this information flows is dictated by like data collection methods and analysis and models. So how does the complex human system receives, advice usually that flows through some sort of models, and then those human modifications flow through policies or laws, or sometimes just individual behaviors. But we can't ignore that there's a ton of uncertainty in natural systems, and we don't understand all of the underlying processes. There's randomness, unforeseen events like new diseases mutating, or catastrophic environmental events. For instance, on the Fraser a few years ago, we had this massive landslide that blocked migration. They're these chance events that you can't really plan for. And then on the human side, human systems are driven by human priorities, which vary widely across people. People have different worldviews depending on their backgrounds. The way that they understand ecological systems may vary widely. Their morals will exert influences on the decisions they make. And then you also have all sorts of stakeholders trying to exert influence on the system and the decisions that are made. Okay, so let's visualize this in a little bit of a different way, and kind of how this might actually happen in real time in one of these systems. So we can build this loop where the top half of the loop is usually done by scientists, and the bottom half of the loop is usually done by some sort of manager or decision makers. So you have data that flows out, it gets analyzed by scientists like us doing forecasting or other sort of analyses, that the advice from that analysis flows out to decision makers, and then that flows back through management, which then inherently has an effect on the natural system. And on some sort of time frame, we generally repeat this loop. As new information in the natural system becomes available, we update our forecasts, we change our models, we adapt to new things that are happening in the environment. So in this schematic, each turn of this cycle has potential to be very much the same or very much different in each turn of this cycle, depending on a number of factors. How rigidly set is each of those loops? Is that locked down? Do we collect the exact same data every year? Do we run the exact same models? Do we have the same decision makers? Or do we have a whole new batch of decision makers with different priorities at every turn of this loop? And on the flip side, you have to think a little bit about the amount of resources that goes into each turn of this loop. Can we afford to do this every year? Every single year, can we collect new data, run new models, give new advice? Or is it kind of more of a turn the crank situation where we don't really revisit what we're doing, we just plug the same numbers into the same model and it passes through that system? So let's walk through a real world example of one of these systems. and what this loop looks like. So obviously, I'm talking about fisheries sciences. So fisheries science is kind of the study of this whole system. It's not necessarily just the study of the fish population, it's the study of this whole paired system. So what happens in the top half of this loop is usually what we call stock assessment. So this is where we're assessing the status of some kind of fish stock. So information comes out of the fish stock and gets analyzed in some way that creates advice. That advice turns into some sort of management. So let's start first with that first information flow from the fish stock to scientists. So I already touched on this a little bit in my other intro talk, but we have generally two distinct types of data. We have fishery dependent data first. So this is catch and biological data reported by onboard observers, automated monitoring systems, portside surveys, something called creel surveys, which is where you go and you talk to fishers and you ask them how many fish they caught, how long did they fish for, that kind of stuff. And then sometimes we dig way back into like historical landing records. So we can go back 100 years and see how many fish were caught in the past. And then we can use this information about catch to kind of infer something about the natural population. Alternatively, we have fishery independent data. So this will be any sort of research survey that doesn't involve just enumerating catch. I talked in my salmon talk about all the fun ways that we count spawning fish as they come up the river. That's me on the Harrison River holding a gigantic fish. This particular stock produces fish about 1 meter long, and we do mark recapture on the spawning grounds to try to enumerate them. So we have all kinds of ways that we get information. Okay, so what do we do with this data? What's kind of the next step? How does that information turn into advice? So kind of in a normal stock assessment regime, in general, you're kind of gonna estimate what the population looked like over time. And this is gonna take in I'm not gonna delve into what any of these models actually look like because there's such a wide variety of them, but essentially the output is gonna be some sort of estimate of what the population looks like over time and its current status. So based on what we learn about the population and its biology and its demographics from that, usually we overlay some sort of reference points, we call them. So this is pretty much saying if the population is below this level, it's bad. Things are above this level, it's good. And it's pretty much that straightforward. So usually on the lower end, you're trying to avoid some sort of risk of extinction. At the upper end, you're aiming for this thing called maximum sustainable yield. So this is that sweet spot in a fish population where all things held constant, which we know doesn't usually happen, but hypothetically, it's a level you could fish at indefinitely into the future and maximize your yield over time. So that's kind of the gold standard upper benchmark that we usually aim for. So yeah, like I said, these benchmarks infer some sort of status. So you'd see that in our last data point there in our most recent year, we're kind of in the yellow zone. Things aren't too bad, things aren't too great. We usually call this like the cautious zone. Okay, so that's great. We know the stock is kind of in the cautious zone, but how does that turn into some sort of fishing regulation? So in Canada, we do have a framework to guide these decisions. And this dictates that we need to have that lower benchmark we generally call a limit reference point. You'll see LRP maybe in this talk. And in general, we're advised to manage stocks kind of in this way. When a stock is below its LRP, we minimize fishing to the extent possible, which is a little fuzzy. It doesn't say no fishing, it says minimize to the extent possible. You ramp up in some way up until your kind of maximum harvest level if you get into that green zone. And it seems pretty cut and dry. Like it seems like it'd be pretty easy to plug these numbers in, but the policy doesn't actually dictate. Like it doesn't say zero fishing below that LRP. It just says limit to the extent possible. It doesn't dictate how that ramping up looks. It doesn't dictate what that upper fishing point is. So these are all things that are up to scientists and managers to figure out together. So some of the guidance we do have recently, the Fisheries Act in Canada was amended to include fish stock provisions, which lay out these guidelines for us. Fish stocks must be managed at sustainable levels. Stocks that fall below their lower reference point require rebuilding plans. So that's a big process where we write a whole paper about what we're going to do, but it doesn't lay out actually in a management side exactly what's to be done. It just says you got to look into it. And it says LRP should be adequately precautionary as to avoid serious harm. So as you can see, like this helps a little bit. And as fishery scientists, we look to this and we cite this and we try to fit in this framework, but it doesn't really exactly lay out exactly what we should do here. There's still a lot of wiggle room about how we're going to do that analysis side and how we're going to do that management side. Okay, so let's come back to looking at this cycle as a whole, just to get an idea of what this whole management cycle looks like. So like I mentioned, data flows from the natural population through a wide variety of methods of data collection, and then scientists take that information, run some sort of models to infer some sort of status and give some kind of advice to managers. And the managers have this framework, but quite a bit of wiggle room to say, okay, given that status, what are we going to do? They send the fleet out, they go fishing, that affects the population, we do the loop over again. So usually this loop is kind of done about on a yearly basis. And it's pretty resource intensive, collecting all this data, running all these models. And it also, like I mentioned, because that harvest policy isn't set in stone, it has the potential to look pretty different year to year, what kind of actual management action comes out of there. Okay, so let's think of some of the pitfalls of this. Bias in data, of course. Missing data, that's a big thing. I mentioned in my other talk, we have these like fish counting fences in high water events. They can just get blown away. It's just thousands of dollars of equipment blown down the river. It happens, missing data. The pandemic caused lots of data gaps. We just couldn't send our field crews out because they couldn't stay in camps together. So yeah, missing data is a big issue. And another huge issue we're seeing, and this is really pertinent to the case study, is stocks changing rapidly, and we're kind of in this unprecedented climate. So we kind of saw our stocks bouncing around in somewhat of a predictable way, and then in the last 15 years, all of those models kind of, went down the toilet and don't work great anymore. And then on the, well, that one carries over kind of actually into this node. But so like I mentioned, poorly fitting or uncertain models. And then another big breakdown that can happen here is ineffective communication between scientists and decision makers. So this requires that scientists explain the models they've used, they explain the inherent uncertainty and all of those things. And sometimes that communication isn't awesome. And sometimes managers don't fully comprehend kind of the uncertainty involved. Okay, and then like I mentioned, when managers actually get that advice, there's nothing holding their hands to follow exactly what scientists recommend. There's all sorts of outside influences needed against advice. And then sometimes these decision makers or stakeholders that might be involved in decision making have conflicting objectives, which somehow then kind of dilutes that information as it goes around the cycle because it's filtered through their worldviews and their objectives and their morals and all of those things. And then kind of there's kind of one more bit where this can break down, and that's imperfect application of regulations. Fishers don't always comply. People really love catching fish, and even if fisheries are closed, sometimes they still go catch fish. So it's something we have to consider, that there can be considerable bycatch in wrong fisheries, also illegal fishing, people just not following regulations. Oh, and another thing that's kind of interesting too that can throw this off is there's sometimes cases where there'll be a stock that is in a good place, and we'll say, okay, yeah, go ahead, fish. But then the market price is so low that the fishers are like, yeah, no thanks, like we don't want to. But we've built into our models that they're going to be fishing, and then they don't. So you can't always count on them, following what they're allowed to do. Okay, so. Yeah, this is happening earlier than I thought, so we're going to do this first. Okay, so now it's time for us to put our thinking caps on. There is not a single equation in this talk, so don't worry, you're not going to have to do any math at all, but I want to do kind of an interesting brainstorm. So I want to come back to this general case where we're not just talking about fisheries, we're talking about any paired system, with some sort of complex environmental side or complex natural side and some sort of complex decision-making side. And what we're going to do is this exercise called a 1, 2, 4 all. So has anybody heard of liberating structures? Okay, so essentially they are techniques for like idea generation and getting people talking in like a structured way rather than just being like, talk to the person next to you, because that doesn't always work. So it's a little bit more structured than that. So what we're going to do first is you're going to spend 2 minutes alone generating ideas, 4 minutes in a pair where you share what you came up with and you give each other feedback, and then in groups of 4, you're each going to talk about what you came up with. So essentially what I want you to do is identify a paired human environment system that you have some familiarity with. And you don't have to have full familiarity with this at all. It could be something from your case study. It could be something from your hometown that you know is like an issue there. Like one hypothetical example that I was kind of thinking through when I was doing this talk is like, think about like a dam that's holding up water in a reservoir and that decision of how much water to let through. That's kind of a fun hypothetical situation to think through. You could think about land use, how you're going to use, there's a forest and there's kind of competing objectives about what to do with that land. So just try to think, and you're going to have 2 minutes to do this on your own. Try to think of some sort of paired system, and all the health science people here too. This can be a health science thing too, right? This can be some sort of disease system paired with a decision-making system. So don't think that this just has to be fish or trees or water just because that's what's in my cute little icon. So I want you to try to fill out each of these 4 nodes and describe what flows between them. And then for each of those 4 nodes, some sort of challenge that might cause that link to break down. How does that sound? Okay. Okay, so let's do 2 minutes on your own. I should have had like organized to have like clipboards or something. I'm sorry. So maybe just if you could scribble down notes on your computer, maybe if you don't have a notepad. And let's do 2 minutes and see how we do with that. Jesus. That kind of help you develop your ideas a bit more? Okay, kind of? Okay, awesome. Okay, next step, reshuffle. Now you're in groups of 4, and I just want you to each kind of share your cycle you came up with in the groups of 4. No, try to reshuffle. Try to get away from that person that you were with. Yeah. Yeah. Get the heck out of there. Yeah. Yeah. My manager. Oh, am I on? Recommended. Experimenting on humans, not usually recommended. And we also want to, like, this is a forecasting course after all. We want to look ahead. We don't want to just look at the current state, like what's actually going to be effective in the future. Anything else someone would want to add to their management framework wish list? Did I nail it? Okay, so I think we're going to do a break pretty quick here, but I'm going to leave you with a teaser of what's to come. So I want to present an alternative to this kind of yearly cycle of information and advice flow, what we would call in a broad sense, a management-oriented approach. So a management-oriented approach, rather than focusing on the estimate of some sort of indicator metric and kind of keep up with the current status of the system and respond to that on some sort of time step. So our fish is doing, our population is doing poorly, let's do this. Let's make a decision based on that status. Let's actually step back and identify an entire management procedure that performs best when it comes to policies and objectives and when faced with those uncertainties and challenges. So in fisheries management, we call this management strategy evaluation. And what this is a participatory decision-making process that allows us to test drive management procedures using forecasting and scenario testing. So that's what we're going to talk about after the break. So I think we're going to do, we'll do 20 minutes? Like, yeah.
And we're going to have a picture coming up. So if you guys want to, we're going to have a little break. Let's say actually at 11:20. Yeah, so let's say at 11:20, we'll meet you guys outside. And then oh yeah, sorry. Which direction? Yeah. There's two. I think by the water, that one might be nicer. So let's go outside of that.
Okay, so just as a refresher, we went over that kind of like maybe yearly cycle feedback loop of managing that paired system, but now I want to suggest a slightly different approach, which is more of a management-oriented approach. And in fisheries management, we call this management strategy evaluation, which is a participatory decision-making process that allows us to test drive management procedures using a mix of forecasting and scenario testing. Okay, so what does this look like? Okay, so rather than the first step of that loop just being scientists collecting data, we consider the whole system from the start, because there's a whole lot more information we need to collect for this analysis than we do just to assess the health of the stock. So the first step brings together, of course, still biologists collecting information about the stock, but it also we need to learn information about the system, like in this case, we call them fleet dynamics. So the dynamics of the fishing system, the dynamics of the management system, what kind of constraints there are, what sort of uncertainties there are between each of those nodes. So that first step is like a much more integrated first step. So we gather information on the whole system, and then the next thing that's really important is we identify objectives. So this is where those stakeholders come in key, and they come in at the beginning. So rather than talking about objectives in that management step, which turns out to kind of be the third step, that's at the very beginning, and it's at the core of this analysis, or who are the stakeholders and what are their objectives? Because spoiler alert, we're going to simulate the whole system. We're not just going to estimate the population, simulate the population, we're simulating the whole management system. And there's going to be a lot of back and forth in a lot of these steps, because oftentimes stakeholders and decision makers don't know what they want to see to make a decision until they see what they don't want. Does that make sense? You'll bring something to them and be like, here's the information to make your decision. And they're like, no, that's not what I want. So all of these steps have a lot of feedback, because we have to identify objectives, build that into our simulation, and then we have to come up with some kind of outputs that allow us to make a decision about the system as a whole. Okay, so who is involved? So this is just kind of often what this looks like. Usually we have some sort of scientist, manager, working groups, and that's really who's getting at the core of like building those simulations. So these will often be scientists and technicians who collect data, modelers, and resource managers. So those will be, so for me, working at Department of Fisheries and Oceans, this would be someone like me, plus the people who collect the on-the-ground data, maybe some biologists with really specific information about the stock of interest, and then also resource management folks who can tell us more about the actual management of the system. And then kind of another piece, and I mean, we bring together all these people, but this usually happens in a slightly different setting, are getting together those representative stakeholders. So these will often be like recreational or sport fishery interest groups. So often sport fishers will hire people to essentially lobby for their interests. So we're not necessarily having like a sport fisher come to every meeting. We're usually having like a representative of some sort of organized group of sport fishers that want to see their objectives brought into the equation. This will definitely include Indigenous groups on the West Coast because they are big stakeholders in these fisheries. A lot of these fisheries represent their way of lives, their livelihoods. So they're definitely going to be there. Often you'll have people from conservation organizations or environmental non-government organizations, so people who are really interested in the conservation of ecosystems and specific stocks. And then, of course, commercial fisheries representatives. Sometimes it's the actual commercial fishers in certain cases, but more often it's kind of more similar to that sport fishery case where they actually hire people to kind of lobby for their interests and make sure that their kind of objectives are known. So what information do we need to pull off this big simulation? So, and not just the simulation, the whole process, but we need kind of the same step as we would in the other cycle. We need stock assessment, data, and models. So we need to have some sort of like demographic information. We need to have information about the history of the stock, all that kind of biological stuff. But then we also need to know about fishery dynamics. We need to know what catch has been. We need to know what we call harvest rates. So it's usually like the percentage of the stock that is harvested given some sort of level of effort. There's also something called fleet dynamics, which is just kind of like how the fleet of fishers works. Like, where are they located? How many boats are there? What kind of gear do they use? Like, all of these things can kind of build into this simulation of how we apply some sort of management regime and how it actually plays out for the stock. And then we need those management objectives. And these are just some examples. So this is what I'm talking about when I talk about like those stakeholder processes. Like, what do we want? So, you know, fishers probably want to achieve maximum sustainable yield. They want to get the population to that point where we can keep fishing well every year. We want to prevent overfishing, and we want to prevent any sort of risk of extinction. Some fishers really value catch stability. I mentioned a little bit earlier about like market prices, and big fluctuations in market prices for fish can be dictated by big fluctuations in supply. So fishers, to make things easier for them, they want to have like a pretty stable catch over time because they don't want to have to, on a big run year, go and buy a bunch of new nets, for example, or have to go buy another boat. They want to know, they want to like kind of see, they want to know what to expect. So catch stability is actually surprisingly important for fishers. We might want to conserve population structure. So we might be really concerned about, some of you have maybe heard about the cod collapse that happened some years ago. And, you know, we found that the population structure kind of collapsed. We lost all the big individuals. We fished the crap out of them, and we just haven't seen that bit of the population come back. And then we're also bound by things like meeting allocation or treaty requirements. So we are legally bound to give Indigenous fishers first rights to stocks within their territory. So all of this kind of lives in the bounds of things like that. Okay, so I alluded to this simulation before. So what does this simulation we run look like? So we run what's called a closed loop simulation, which means there's feedback at every step. So within that, we have what we call our operating model. So this is what we call the true abundance of the stock and the true catch. So we're imagine like a snow globe, and we're like pretending this is the true state of reality. And this is kind of where the forecasting step happens, because this is where fish grow, reproduce, die, some sort of catch is imposed, it loops around to the next generation. So this is kind of happening, you know, in a petri dish, essentially. And this is what we can kind of test out our management strategies on. So out of this operating model, we try to approximate like what we would actually get out of it. So we produce survey data or fishery dependent data based on what we know about the system, based on what we know about, you know, how much of the population we can actually sample, what sort of observation error we might have, you know, maybe different levels of bias we might try out. So we simulate kind of generating data from this petri dish true population. And then we take that and we do that stock assessment thing I was talking about before. And then out of that stock assessment, we come up with we impose our harvest control rule, we call it. So these are essentially what we're testing out. We're kind of testing out like different ways to put these benchmarks. Are we going to do it in this way or a different way? We're testing out different scenarios of how we're going to manage the whole stock. What is that stock assessment going to look like? What are those benchmarks going to look like? How are we going to react to the population being above and below those benchmarks? And then that loops back through harvest policy. And then of course, in that step, we need to make sure we account for implementation error, because the fishers aren't going to fish exactly what we tell them to fish, right? Because a lot of these fisheries some of them are managed to a number of fish or tons of fish, but some of them are managed by effort. Like if any of you are recreational fishers, you know that there's certain times of year, certain places you can fish. So if we're controlling effort, we're going to have some uncertainty about exactly how many fish they're going to catch. So we have to account for that in our implementation error, we call it. Okay, so let's zoom back out. Where does this actually fall in the entire process? Because the model isn't it. I mean, the model is the part that probably we're pretty interested in because they're cool models, but this is just like one piece of this fully integrated process. So we've elicited all the information we need about objectives. We've built this whole simulation. We've tested out a bunch of different harvest control rules. Okay, now what do we actually spit out on the other end? So lots of different things. On the most basic level, you might get some time series going forward of so each of these lines would represent a different harvest control rule. So it could just be a different shape of that kind of ramping up of fishing. It could be just a flat fishing rate. It could be something totally different. You can dream up any harvest policy you want. And we can look forward in time and see, okay, let's simulate the population and that harvest control rule forward and see where we end up in a certain number of years. And of course, there's going to be error bars around these, but I didn't put any. Often you want to summarize these in certain time frames. So we might be interested in looking at like a short-term time frame, which might be like 5 years. A medium term might be like 10 years. A long term might be if you're looking 20 years down the road. So we might say, okay, this is some sort of performance metric. Let's say this is catch. So let's look across these 3 different harvest control rules. If we're looking short, medium, long term, what are kind of the trade-offs between those 3 harvest control rules indicated by the different colors? Oh. I am not going ahead a slide. I think there was a bunch of hidden animations in there. It's working. I don't know what happened to them. Okay. And then we might get really fancy. And this is kind of just like a cool, I mean, none of this is really need to know, but this is just kind of a cool example of the type of plots we use. So in fisheries, we like to make things as confusing as possible by using words that are nearly the same. But we like to talk about a stock being overfished versus being in a state of overfishing. So on our x-axis here, that's SSB as spawning stock biomass, which is just kind of an estimate of the total mature population size. So this is usually measured in tons. And we look at spawning stock biomass divided by some reference point. If that's below 1, it's bad. If it's above 1, that's good. And then on the y-axis is kind of like a target fishing rate. Are we below the target fishing rate or are we above the target fishing rate? If you're above the target fishing rate, you are currently overfishing. If you are below this target, you are in an overfished state. Pretty much you're in like a poor abundance state. So we can look at these things called Kobe plots, which are pretty cool. And when you simulate forward in time, you move around through these quadrants and you can look at where you are over time. And it's kind of cool because you can see how responsive your harvest control rule is to the stock ending up in a bad place. Like, does it kind of get good and then whoops, it goes back, or is it able to kind of right the ship and get back to a good place? And here we often see, I've heard it called lots of things, but often things like vortex of doom or something, because it's pretty usual that you'll have a simulation that'll like do this loop around, end up in that red zone, and then just circle, 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 and go kaput in that red zone. So you want to avoid that. Again, I think there's a bunch of animations here. Okay. But remember, we don't really want to think about this like one metric at a time, right? Because we're balancing a bunch of objectives, and depending on the stakeholders involved, these objectives can be different. We might all want healthy ecosystems and healthy fish stocks, but some people might be more concerned about things like food security, maximizing catch, having stable catch, meeting legislative requirements. So how can we consider these all at once? So a common tool we use to assess these trade-offs is using these spiderweb plots. So you'll see these again a little bit later. So where each vertex of this hexagon is a different performance metric, and then each kind of web on there that's a different color is a different harvest control rule. So you can see different how different harvest control rules performed. So like the red one is like really awesome when it comes to metric 2, but like not so awesome when it comes to other ones. So this is like a great way to show how different ones meet different objectives and how the trade-offs are. Okay, let's zoom back out. Let's look at the whole system again. So we've gone through, we do this big information collection exercise. We build this awesome closed loop simulation. We test out a whole bunch of harvest control rules. We make a bunch of spider web plots. We sit down with decision makers and probably stakeholders, and what now? So essentially, you hope that after going through all of this, you've got pretty significant stakeholder buy-in. They feel like their voice is heard. We've looked at all the trade-offs together, and hopefully they can come up with some sort of policy. So what flows in that last step, where in the other version we were looking at before, what gets spit out is just a decision for that year, right? Essentially, is you look at the status of the population, you're spitting out a decision for the year that gets looped around. Here, you're actually, at the end, you're producing a policy, right? And it's a policy that you're hoping will be stuck to and used in the future. And I also want to mention too this feedback loop here. Like I mentioned before, stakeholders and decision makers don't often know what they want to see until you show them what they don't want to see. And often this process of coming up with these different harvest control rules gives more ideas. Like, okay, well, you really like that harvest control rule. I like this one. What's somewhere we can meet in the middle? And often that iterates a ton, going back and trying out new things. Okay, so does this tick the boxes? So is it objective and transparent? Hopefully. Hopefully, if those involved are managed to stay objective and transparent, as long as it's well documented and stakeholders put all their cards on the table. That's a really key piece, right? Because if they don't put all their cards on the table and you get to that last step where you're considering all these different harvest control rules and you say, doesn't this one look good? It matches your objectives, and all of a sudden they say no. It's like, well, you probably weren't actually honest about what your real objectives were. So, and I mean, on the flip side, I think there's often cases where people find out they have shared objectives, right? Like you kind of think like someone from a conservation organization and a fisher would be against each other in terms of their objectives, but they both want healthy, productive fish stocks. So often there's ways, to find common ground. Okay, adequately protect the population from conservation risk. I mean, hopefully, as long as we value those harvest control rules that do that. Balance objectives of multiple stakeholders. I think so. I think this is kind of like one of the best ways we can do that. Take into account uncertainty, as long as you've identified all of your uncertainties and you've modeled them decently well, hopefully. Ideally, it can be tested without having to experiment on real populations. Yes, that's a real strength here, is that we're test driving in a virtual setting. We're not actually, fishing the crap out of a stock to see what happens. And it looks ahead and not just at the current state. So that's a real strength of this too, is we're not just simulating a population forward, we're simulating an entire management system forward. So it does look ahead, and you can overlay things like climate projections and stuff onto these. So. Okay, and I already alluded to this, but I think probably the biggest benefit of this sort of approach is seen in terms of stakeholder engagement and buy-in. So there can be a lot of resentment built up when management in the system is top down, and stakeholders don't have a say until the decision's essentially been made and is coming down from the top, right? Like we talk about, consultation. Consultation usually happens after really a decision's almost been made. So in this case, there's buy-in from the beginning. They get to get in each other's shoes, kind of. They get to see the decisions facing a manager. A manager gets to see their objectives, hopefully that they've fully laid on the table. And it's a little bit easier to kind of come to an agreement in this way. And it might seem impossible that in the last step there would actually be consensus with all the competing objectives, but like I said, when everyone gets to see the whole picture, usually that is much more likely than in a different kind of framework. Okay, but it's no silver bullet. I know I'm like selling this as being a great thing. With all buzzy, tools of the moment, it takes a little while for like the cracks to reveal themselves. And we've been kind of doing MSc long enough that, the cracks have started to sort of reveal themselves. It requires, even though that buy-in from stakeholders is a huge benefit of it, getting that buy-in in the first place can be really hard because it requires building trust, relationships, requires a lot of time, effort, and I mean, time is money, right? Like a commercial fisheries, like a conglomerate of commercial fisheries might have a budget to send like a really awesome person to lobby for their interests, where a First Nations organization might not have those same resources. And asking someone for their time in that way, if you're not willing to pay them, is not really equitable, right? So you have to make sure that you like actually have the budget to bring everyone to the table, because it's easy to miss stakeholders that don't have an economic interest in it, right? So yeah, that's one of the big challenges of this. Second, each of those complex systems kind of like needs to be tractable. We need to be able to model them. And that can be hard. So some of the challenges in fisheries are like transboundary stocks. So imagine a case where you're trying to build this framework for a stock that hangs out right on the border. And you're trying to plan for the Canadian fishery, but the American fishery is catching them too. And they're making their own decisions. They've got their own framework. So transboundary stocks are like a huge issue. And that's why we have lots of treaties to do with fisheries. Mixed stock fisheries are another challenge, which is a big challenge in salmon. Often you're not just fishing one stock. So you've got multiple populations you're targeting at once. Some might be in really poor state, some might be in a better state. So that is something that can be really challenging. You can have really complex ecosystem feedbacks too that are unforeseen. And then in more general sense, kind of the same thing. You could have tipping points. I won't draw the ball in the cup, but that. And then other just like chance events that you might not be capturing in your simulation. So I wanted to mention that a few years ago, I was part of an MSc that fell apart, and it was because of these reasons. It was on a set of salmon populations. Each population had its own stakeholders. You're trying to figure out who to get at the table. You realize you've got the wrong people at the table. You're missing some people. Those people who are at the table aren't able to clearly name their objectives. That some of those stocks, their management is dictated by a treaty because they're transboundary. We couldn't get what we needed from the stakeholders. We couldn't successfully model the system. It just didn't work. It doesn't always work. Okay, cool. Let's play a game. So you should be able to find this link either in my PDF presentation if you've pulled recently, or just go to the GitHub and I put the link in the README, in the schedule. It's like, when you go to the main GitHub page, there's the schedule and the README, there's a link there. Okay, so what this is just like a fun little shiny app that was developed by one of my colleagues during her PhD. So it's like a little old. You'll notice the like most recent data point I think is like 2015 or something. But I just want to like give you a chance to actually play with some of these things to kind of like get an idea of like what it can do.